Welcome back to my channel. Today we're going to be talking about derivatives of inverse functions. So, there are a couple different things that we have to keep in mind when we're talking about the derivatives of an inverse function. So, let's kind of get through these three different methods. So, the first method is when you are given an equation for f of x, and you can find the equation for the inverse pretty easily. So, we are going to be looking at these problems, trying to find inverses and see what we can do. So when we are finding an inverse, what we're doing is we're finding the function that is kind of the complete opposite of it. And what that means is when we plug an x value into one of our things, it's going to give us a y value, and that y value will give us the x value in the other equation. So when we look at a function like this and we need to find inverses, we may be given a problem like, let f and g be inverse functions where f inverse of x is equal to g of x. If f of x is equal to x cubed minus 1, then find g prime of 7. So x cubed minus 1 is something that we can kind of work with. So the first thing that we're going to do when we try to find an inverse is I'm going to go ahead and change it to x's and y's. So y equals x cubed minus 1. We have an inverse function when our original function is reflected across the line y equals x on a graph. So when we do that, what we're going to be saying is, well, x equals to y and y equals to x, so we're flip-flopping our x's and y's. So what we're going to do is we are going to change which one x is and which one y is. So x is equal to y cubed minus 1. So now we're just going to try to get y by itself. So I'm going to add 1 to both sides, so we get x plus 1 equals y cubed, and then I'm going to take the cubed root. So we have the cubed root of x plus 1 is equal to y. Well, this function right here is g of x, so g of x is equal to the cubed root of x plus 1. Okay, so when we want to find the derivative, we need to find the derivative of this function. Before we do that, we're going to go ahead and change what this looks like. So I have x plus 1. The third root is the same thing as raising something to the 1/3 power. So I'm going to take the derivative of x plus 1 to the 1/3 power. So I have g prime of x is equal to 1/3 times x plus 1. Now we take 1 away from that power, so if we take 3 over 3 away from 1 over 3, we get negative 2/3. And then we would want to multiply this by the derivative of the inside. The derivative of the inside is x plus 1, so the derivative of that is 1. So we multiply all of this by 1, which we don't actually have to. So I'm going to rewrite this because we're going to be plugging in 7. So I have 1 divided by 3 goes in the denominator. Our x plus 1 has a negative with it, so I know x plus 1 is going to go in the denominator, and that 2/3 makes it the third root of x plus 1 squared. So now what we're going to do is we're going to go ahead and just plug in 7. So g prime of 7 is equal to 1 over 3 times the cubed root of 7 plus 1 squared. 7 plus 1 is 8. If I square 8, I get 64. If I take the cubed root of 64, I get 4. So this is going to be 1 over 3 times 4, which happens to be 12. One of the reasons why this method is not necessarily the best method all the time is because it takes a while to do this, and because we're keeping the AP test in mind, speed is always a factor. So some of these other methods might be able to work for things that we have, but sometimes they don't. So this one is like, if we can find the inverse, we are good to go. Okay, so if f of x is equal to e to the 2x, find the derivative of f inverse of x at 3. So the first thing we're going to do is find the inverse of this equation. So y equals e to the 2x. So I'm going to go ahead and flip-flop x and y. So x is equal to e to the 2y. So the first thing that we're going to do is we are going to do the natural log of both sides to kind of get rid of this this exponential base of e. One of the things that we have to keep in mind, though, is that our x values are very limited once we can incorporate natural log. So we're going to actually take the natural log of the absolute value of x to kind of help us out here. So the natural log of the absolute value of x is equal to the natural log of e to the 2y. We don't need a absolute value for this one, only because e to a power, as long as we don't have a negative in front, is always going to be positive. Because e and natural log are the inverses of each other, we are left with whatever is in that exponent, and that exponent happens to be 2y, and then I'm going to divide by 2 or multiply by 1/2. So I have 1/2 natural log of the absolute value of x equals y. So what I'm going to do now is I'm going to take the derivative of this. We now know that f inverse of x is equal to 1/2 natural log of the absolute value of y. 1/2 of the natural log of the absolute value of x. And now I want to take the derivative of this. So f inverse prime of x. 1/2 stays where it's at. And we are going to do the derivative of 1 over x, which happens, or of natural log, which happens to be 1 over x. So this is really just 1 over 2x. Now we're going to plug in 3, so f inverse of x prime is equal to 1 over 2 times 3, which equals 1 over 6. So just like before, this just takes that algebra knowledge of knowing how to find an inverse, how to use the inverse, and things like that. It's not terribly difficult, but it can be kind of just a process, and it might take a little bit longer. Method 2. So you are given an equation for y equals f of x, but finding the inverse is difficult or impossible. So sometimes we are not able to find the inverse, so we kind of just have to take what we can. So find the derivative of our inverse at x equals 1. So find the inverse relation. So we're going to flip-flop x's and y's, but we're not going to actually solve for x, or for y. So my original function was x cubed plus 2x plus 1, and I'm just flip-flopping them. So x is equal to y cubed plus 2y plus 1. Now I'm going to take the derivative of both sides using implicit differentiation. So we're going to want to do dy over dx. So the derivative of x is 1. We have 3y squared dy over dx plus 2 times dy over dx plus 0. This is going to be now in terms of y. So we need to figure out what our y value is. So one of the things that I'm going to do is I'm going to try to get my dy over dx's by itself, so that way I only have one of them, and then kind of go from there. So we have 1 equals 3y plus 2 times dy over dx, which means 1 over 3y plus 2 equals the derivative dy over dx. So one thing that we have to keep in mind is that y is just what is our y value. So we're going to take our original function and x equals 1 and plug it in, so that way we can figure out what our y value would be. So f of 1 is equal to 1 cubed plus 2 times 1 plus 1. So 1 plus 2 plus 1, which is 4. So I know that I can go ahead and plug in 4 into our problem. So now dy over dx when y equals 4 is equal to 1 over 3 times 4 plus 2. Ooh, I dropped a squared. So 1 over 3y squared plus 2. So 1 over 3 times 4 squared plus 2. So we have 3 times 16. 3 times 16 is going to be 3 times 10 and 3 times 6. So we have 48 plus 2, which happens to be 1 over 50. Huh. So we can kind of deal with this. It's one of those things that we'll just kind of get it into whatever variable we can. If I have x's and y's for some reason on this side, I'm going to just plug in 1 for my x and 4 for all of the y values, and then kind of go from there. So that's good for things where we don't have x's with everything, so I couldn't factor anything out. It also is good when we have two different types of functions kind of put together, like an exponential and a polynomial. So find the derivative of our inverse. So same kind of a thing. I'm going to go ahead and switch my x's and y's. So I have e to the 2y plus 3x, which is now a y. So I'm going to go ahead and do the derivative with respect to x. So 1 is equal to, the derivative of e to the 2y is 2 times e to the 2y, because the derivative of 2y is 2. And then we have dy over dx that we multiply by it. The derivative of 3y is 3 dy over dx. I'm going to do the same thing where I get dy over dx by itself. So I have 1 equals 2e to the 2y plus 3 dy over dx, and 1 over 2e to the 2y plus 3 equals dy over dx. So now same thing, I just need to plug in my x value of 0 into g of x in order to get my derivative. So we have e to the 2 times 0 plus 3 times 0. Well, 2 times 0 is 0. E to the power of 0 is 1, and 3 times 0 is 1. So I'm going to be plugging in 1 to my function. So dy over dx when y equals 1 is equal to 1 over 2e to the 2 times 1 plus 3. Well, we can't really simplify that a lot, so it's just 2 times e to the second power plus 3. So the one thing that I would probably do is just either leave it like this or use notation. The notation's a little bit weird because it doesn't tell you what other functions, so you would have to write something like f inverse prime of 4 is equal to 1 over 50, or g inverse prime of 0 is equal to 1 over 2e to the squared, 2e squared plus 3.